Hello, my name is Alexis Widdifield. I am a graduate student from Coastal Carolina University in the Masters of Arts and Liberal Studies program in Conway, South Carolina in the fall 2020 semester with the help of Dr. Carolyn Dillian and Dr. David Palmer as an extension of their 2018 research project on the manufacture of brick in historic Brook Green. I tested the chemical composition of low-fired earthenware ceramic artifacts that were excavated during the 2016 field school and compared them to the chemical composition of clay sources that were taken from the grounds of Brookgreen Gardens. It was our goal that this research can serve as a model for the application of X-ray fluorescence spectrometry in historical archaeology provenance studies and can answer questions about the lives and livelihoods of African and African American people that were held in bondage on plantations across the American South. For the last 5 years, Coastal has worked with the nonprofit Sculpture Garden and Wildlife Preserve Brook Green Gardens in Georgetown County, South Carolina. The gardens include the remains of Brook Green Plantation, as well as 3 other historic rice plantations. The property of Brook Green Plantation contains historic archaeological resources associated with enslaved African American, and Native American people. The remains of Brook Green Rice Plantation are within the publicly accessible areas of Brook Green Gardens today. Prior to the 18th century, the property that became Brook Green Gardens was first occupied by Native American people. In the mid-18th century, it was purchased by English colonists, and under the ownership of Joshua John Ward, Brook Green was expanded to be one of the largest rice plantations in the United States. After the end of the Civil War, the people that were held captive on Ward's plantation were emancipated, and rice cultivation ended soon after. Since 1932, Brook Green Gardens has been open to the public as a nonprofit exhibit for figural sculpture, and in recent decades, archaeologists have begun to study it in terms of the history and cultures associated with the property. Colonoware ceramics are handmade, low-fired, unglazed, and unrefined earthenware produced from the mid-16th through the 19th century. Colonoware as a category covers a broad geographic and decorative range. The term describes an archaeological type of handmade ceramics that were stylistically influenced by Native American, African, and African American manufacturing processes. Ceramics were being made on the southeast coast prior to European contact, but colonization forced changes in the manufacture, form, and clay sources that were used, and the result is Colonoware. Archaeological evidence of kilns that produced Colonoware and low-fired earthenware is scarce due to the efficiency of the manufacturing process. Colonoware ceramics were often fired in open hearths, such as cooking hearths, at lower temperatures, so they could have been produced at many places in historic Brook Green. Clay consists of mostly fine particles of hydrous aluminum, silicates, and irons, alkalis, and alkaline earths, with varying mixtures of water and organic material. The porous texture of Colonoware differentiates it from ceramics that are fired in enclosed kilns. Native American tribes would typically use processes such as open firing, bonfire, or the clamping method in ceramic manufacture. Pots would be stacked on top of each other on the ground or in a shallow pit in direct contact with fuel. And this process entailed making a bed of slow burning fuel placing pottery over the bed and covering the pottery with a top layer of morphine. Prior to firing, the molded containers were dried thoroughly, sometimes for weeks, depending on the climate. In the beginning of the ceramic firing process, the gradually rising temperatures evaporate any excess water remaining from the clay. As temperatures rise during the oxidation period, carbonaceous materials are burnt out of the ceramic. And once reaching temperatures of about 600 to 1000 degrees Celsius, the silicates and other clay constituents soften and fuse together during vitrification. This process burns any organic material from the ceramic, but the chemical composition of the clay remains mostly intact, particularly for the elements that are focused on in the study. The elements that are focused on are iron, strontium, zirconium, rubidium, barium, and yttrium. The chemical composition of clay is a product of changes on the parent rock and sediments mixing through geologic and environmental processes. To best capture the variability within a clay source, 10 dried clay pellets from each location were tested to establish a range of chemical compositions present for the location. Clay was collected using a bucket auger for each of the 6 clay deposits during the May 2016 field school. There were 3 clay deposits that were sampled along the perimeter of Jessamine Pond, as denoted as locations 1, 2, and 3, as well as 3 locations around land that was previously used for rice cultivation as deposits 4, 5, and 6. The clay pellets that were collected were thoroughly air dried over several weeks prior to storage. The use of X-ray fluorescence is becoming more popular in archaeometric studies and is employed in this study for the chemical characterization of ceramics. Portable X-ray fluorescence technology gives archaeologists the ability to analyze subjects in the field or museum and does not require transportation or destructive processing of the specimen. This process allows artifacts to be analyzed as a whole using non-destructive penetrative X-rays. There are different instruments available that have specializations for various fields, but the benefit of handheld X-ray fluorescence spectrometers is that they provide the technology necessary to complete geochemical analysis of archaeological materials in the laboratory or field. An Olympus Vanta X-ray fluorescence spectrometer was used to collect data on the elemental composition of the 6 clay deposits and the Colonoware artifacts. These datum are recorded by the instrument with a parts per million value representing concentrations of each element in the specimen and the standard deviation of each value. The process of recording geochemical composition of an artifact with X-ray fluorescence begins with the specimen being irradiated by beams of X-rays. This displaces electrons from the inner orbitals of the atoms. The measurable and most intense transitions force electrons out of an atom entirely, creating vacant holes that are then filled with electrons from the outer orbitals. This electron transition causes energy in the form of a secondary X-ray photon to be emitted, and this energy is distinct for each element. The instrument reads the spectrum in 2 90-second intervals, testing the parts per million concentrations of heavy, then light elements. Prior to conducting the study, we tested the geologic standard NIST 278 to ensure the accuracy of this data. The instrument detects concentrations of elements from iron to molybdenum But for this study, the focus is on strontium, zirconium, rubidium, iron, barium, and yttrium. Data was collected using the Olympus Vanta instrument and then translated into Excel for Windows. The dataset was narrowed to highlight only the aforementioned elements because of their chemical integrity through ceramic firing. And that information was then graphed using PAST, the Paleontological Statistics software package for education and data analysis. And this was the result of that. Geochemical analysis using X-ray fluorescence was conducted on 60 sample pellets in total from the 6 locations within Brookgreen Gardens. And this helped to provide a spectrum of data that can more accurately represent the range of chemical variability of each location. This graph illustrates the 6 different geochemical signatures of the distinct locations with 6 separate color-coded ellipses. The ellipses represent a 95% confidence interval, and the colored points that correlate to the ellipses are representative of the standard deviation for each of the elements that we're focused on in this study. Artifact data was added to the graph with the individual black points that correlate to ceramic specimens. All of those points, most of those points are graphed in the 4th quadrant, and nearly all of the artifacts that were tested were closely consistent with source location number 2, which was one of the sources along the perimeter of Jessamine Pond. Additional research should be conducted on a larger scale to gain a more holistic understanding of the variation in chemical signatures of the clay along coastal South Carolina. Although the locations graphed in the study are distinct from each other, due to the effects of weathering and sediment mixing, there is overlap in the geochemical composition. Clay source sampling should be conducted to include deposits from neighboring areas. The 3 outliers that are present in the study, shown in quadrant 4, were the smallest specimens that were tested. And that could be the reason why there's statistical outliers. The explanation for this could be that the instrument has difficulty reading the smaller elements or the smaller specimens. The instrument continuously blasts the entire specimen with X-rays to be able to record the elemental composition. So a small sample could potentially cause distortion. Also, the manufacturers that made the ceramics could have possibly mixed clay from multiple locations or added shell or fiber to the clay prior to firing. Thank you all for listening to my project. And just like to make a statement acknowledging that the land on which Coastal Carolina University stands is part of the traditional territory of the Waccamaw Indian people. We honor them and express our gratitude to the ancestors who lived here in the past, the Waccamaw Indian people today, and to the generations to come. And also just a special acknowledgement for Dr. Carolyn Dillian and Dr. David Palmer, who helped me in this project. Thank you.